This is the flip lesson for trig substitution, and I'd like to build your intuition before just giving you formulas. And I thought we'd start with a problem. The integral of dx over the root of 25 minus x squared. We can't use substitution on this, so we have to come up with another technique. It looks something like the distance formula in the denominator. And the distance formula we know comes from the Pythagorean theorem. So let's go down the root of the Pythagorean theorem to try and crack this nut. So we all know the Pythagorean theorem, a squared plus b squared equals c squared, right? Where c, of course, is your hypotenuse. So when I see something like the square root of 25 minus x squared, I could lay down a right triangle and try and define the pieces. Well, if I were to solve for a leg in using the Pythagorean theorem, I would get a c squared minus whatever leg you choose, b squared, right? The square root of it would be that leg. So let's try and lay out on the right triangle. Well, okay, the hypotenuse squared, that would be 25, and the square root of 25 is 5. So I'm going to lay that down as my hypotenuse. And I'm going to put one of my legs here, and then this leg would be the unknown leg, and that would be the leg 5 squared minus x squared. So the angle theta, we can easily solve using our relationships of the legs of the right triangle, but the sine of theta would be the opposite over the hypotenuse, right? Which is simply x over 5. So if I were to solve for x, x is equal to 5 sine theta. Okay, so I've got x's in here. Let's take the derivative of x now with respect to theta, and that's 5 cosine theta. So dx is equal to 5 cosine theta d theta. Okay, now let's substitute. And this concept of substitution in mathematics is incredibly powerful, right? You're taking something more complex or possibly unsolvable the way it is. You make a substitution in the hopes of getting something simpler or solvable. So let's go about and substitute what we know so far. Well, I've got an x, I've got a dx, and I can go about substituting in the pieces into the original equation. So dx is simply 5 cosine theta d theta, and I've got the root of 25 minus x is 5 sine of theta, and then I have to square that. So let's do a little bit of algebra here and see where we go. 5 cosine theta d theta on top, there's not much we can do there. On the bottom, however, I can work algebraically to simplify this a bit, and if I factor out a 25 from below, I see that I've got 1 minus sine squared. And using the Pythagorean identities, I can replace that with 5 cosine theta d theta. I'll just replace that with the root of 25 cosine squared theta. And of course that's just 5 cosine theta in the denominator now, which luckily for us is going to cancel out. And we're left with the basic of all integrals, the integral d theta, which is just simply theta. Well, if I return back up here and solve for theta, I get theta is equal to inverse sine of x over 5. Okay, so I have this answer in terms of x, which is what the original integral was. So the answer would be sine inverse of x over 5 plus a constant. Well, lo and behold, this should look familiar. Right? This is our formula that we saw in the review section 7.1. Well, that's just simply the integral of dx over the root of a squared minus x squared was equal to sine inverse of x over a plus a constant. So somehow we're going to be able to harness the power of the trig functions in order to make a substitution when I see the difference of squares, or the sum or difference of squares, or the root of the sum of the difference of squares. So we're going to go on from here with some formal definitions and work some problems. So now that we've gone through that problem to build our intuition, I want to lay out some formulas for you, if you will. Anytime we see integrals that have terms in them as such as this, the root of a squared minus x squared, the root of a squared plus x squared, or the root of x squared minus a squared, we can use trig substitution in order to really get rid of a sum or a difference of squares and move to products through the Pythagorean identities. Okay, so if we see a squared minus x squared, we're going to use an x equals a sine theta substitution, which we saw in the initial problem that I did. If we have a root of a squared plus x squared, we're going to use a tangent of theta for x, and if we have x squared minus a squared, we're going to use an a secant of theta. So there's 3 trig substitutions that we're interested in. And the goal is to go from sum and differences of perfect squares to products. Okay, so we're going to go from plus or minus to products. And that's going to involve the Pythagorean identities. Okay. So why those substitutions? And as we saw with the problem, the answers lie in the right triangle. Right? So if I were to, just look at this right triangle laid out as such, you could rewrite that as simply this triangle down here, which is what I worked through the problem with you on, and look at the Pythagorean theorem, and the Pythagorean theorem would state that the root of a squared minus x squared plus x squared equals a squared. Right? I mean, that's essentially what it's saying. And if I work all the way through this and do the algebra, I get a squared equaling a squared equaling a squared. So the Pythagorean theorem is at the root of all of these substitutions. Excuse me. So we can work through similar substitutions for tangent and secant. We're going to use trig identities again. We're going to use the unit circle and derivatives of trig functions. We're going to use techniques from 7.3, and as always, we're going to use algebra to help keep things simple for us. So these identities are going to be very important as we move forward with making a trig substitution. And once you make a trig substitution, you're going to end up with a trig integral. Right? And you all know how to solve trig integrals by now after you've gone through the previous section. So once you make that trig substitution, you're going to end up with a trig integral. So we have to rely on, the techniques that we learned from the previous section in order to help us. There's one more identity before I go and do another problem, and that's the double angle identities. I'm going to provide the trig identities for an exam, so you won't need to put them on the formula card. Time for another example. The integral of dx over 81 plus x squared is textbook problem 30. And we've got the sum of two perfect squares, so I'm going to use the trig substitution. X equals a tangent of theta, where a, this is a squared plus x squared, right, is equal to 9, so this is x equals 9 tangent of theta. And dx d theta is equal to 9 secant squared theta. So dx is equal to 9 secant squared theta d theta. So I'm going to pull the algebra aside and work on this denominator, trying to be able to substitute here. So pulling that algebra aside, I'm going to look at 81 plus x squared. Oh, I apologize. This is another square outside here. Squared. Okay, so let's go about and make the substitution for x, and I get 81 plus 9 tangent of theta squared, and then we're going to square that. So this is 81 plus 81 tangent squared theta, and again that quantity is squared, which is equal to, I'm going to factor out an 81, 1 plus tangent squared theta, and that quantity is squared. Now recognize the trig identity. 1 plus tangent squared is secant squared. So this is 81 secant squared theta, and then that squared. So this is interesting because we just went from, and this is what I was talking about in the prior chart, we went from the sum of two perfect squares to products. Okay, so I'm going to write this in terms of power. So this is the same thing. 81 squared is the same thing as 9 raised to the 4th power, and this is secant 4th theta. And I did that so that that'll help with the algebra. Now make your substitutions. So let's make those substitutions. All right, I get, on top for dx, I get 9 secant squared theta, d theta. And on the bottom, I get 9 to the 4th secant to the 4th theta. So cleaning this algebraically and pulling things out, I am left with d theta on top. All right, this is going to, one of these is going to cancel out, and you're left with 3 on the bottom, and this is left with 2 here. So this is d theta over 9 cubed secant squared theta. I'm going to replace this, and you don't have to, but I like to replace this with cosine. It's easier for me to see. So this is cosine squared theta over 9 cubed d theta. So I'm going to pull out the constant, and I'm left with cosine squared theta d theta. Now this is the trig integral that we've seen before, and we know we need to use half angles. So let's use half angles on this. These problems are very lengthy, which is why I need to video as much as I can, or we'll never get through more than just a couple in a class period. So using half angles, I get 1 over 9 cubed, the integral of 1 plus cosine 2 theta over 2 d theta. So I'm going to continue to drag this constant along, and actually I'm going to pull out, you know what, I want to pull out the half here. So why don't I just resolve it? I'm going to pull out 1 over 9 cubed times 1/2. And what remains then is just 1 plus cosine of 2 theta d theta. Okay, so that's easily integrated, and I'm left with the constant multiplied out is 1458, and the antiderivative of 1 is just theta, and the antiderivative of cosine 2 theta is sine 2 theta over 2. Okay, so at this point I'm going to make one more substitution here. So I've got everything in terms of theta. However, I don't know what to do with sine of 2 theta. So at this point, right, because I want to get back to everything in terms of x, but at this point I have everything in terms of theta, so I have to use a reference triangle. But before I do that, I need to make another substitution using double angles. So using the double angle identity, I'm going to rewrite this now, and all I'm doing is substituting in for sine of 2 theta, and this is theta plus the sine of 2 theta using the double angle is 2 sine theta cosine theta, and that's over 2. So the 2's are going to cancel out, and what I'm left with in terms of theta is 1 over 1458 times the quantity theta plus sine of theta cosine of theta. But again, the original problem was in terms of x, so I need to get back to x. So let's get back to x. All right, and how do we do that? Well, we build a reference triangle, and I'll show you what that means. And we did it in the first example, but this is going to be a formal step with all your problems involving trig substitution. You draw the reference triangle. You've got your angle theta, and remember the substitution we used here was x equals 9 tangent theta. And tangent of theta, we all know, is opposite over hypotenuse. I'm sorry, opposite over adjacent. Yeah, we all know that, right? Except when you're tired. Opposite over adjacent. So, if this is theta, your opposite is x, right? Because tangent of theta is equal to x over 9. So the opposite is x, and the adjacent is 9. So what we're left with is the hypotenuse, which is x squared, plus 9 squared. So I built a reference triangle based off of the substitution that we made, and I need to find the values for theta, sine of theta, and cosine theta in terms of x. So I'm going to just use my reference triangle and solve for them. Well, theta, I already know, is based off of this trig substitution that we made. Theta is just tangent inverse of x over 9. So that one was pretty straightforward. Sine of theta is opposite over hypotenuse, and cosine of theta is adjacent over hypotenuse. So sine of theta in terms of the reference triangles is x over the root of x squared plus 9 squared. And cosine theta is the adjacent side, which is 9, over the hypotenuse, which is again x squared plus 9 squared. So let's rewrite this now. Back substitute for x, and I get 1, can't forget the constant, 1 over 1458 times the quantity. Theta is simply tangent inverse x over 9, and sine of theta is x, I'm going to write this out in parentheses and see if we can do some algebra to clean this up a little bit, is x squared plus 9 squared. And cosine is 9 over the root of x squared plus 9 squared. Plus a constant. So I can do a little bit of algebra right here on this piece, and I'm going to clean that up and then call it a day. So the answer here is 1 over 1458 times tangent inverse x over 9 plus 9x over the radical times the radical. You're going to be left with x squared plus 9 squared plus the constant. And that's your answer to this problem.